Hi, my name is Ivanic, and this summer I worked with Dr. Herring K to study irregular signature splitting patterns in arsenic-74. This graph shows signature splitting patterns in various isotopes of arsenic. Arsenic-74 is shown here in light blue. As you can see, most of the arsenic isotopes tend to follow a regular zigzag pattern. However, at high levels of spin, arsenic-74 has a reversed pattern, meaning that when the other isotopes go high, its pattern goes low, and vice versa. Now, a signature is defined by these two positive band structures in this level scheme of arsenic-74. A level scheme is a graph that shows how arsenic-74 will decay from a high energy or a high spin state to a low energy or its ground spin state. And this graph essentially displays the angular momentum along the x-axis, or the spin, and the energy difference between two energy states on its y-axis. However, this graph was based off of measurements that were uncertain. The spin for all energy states on these two bands of arsenic-74 was unknown prior to this study. So my job this summer was essentially to confirm these spins as concrete values. The data used in the study was generated 3 years ago at Florida State University. It was generated by the reaction of carbon-14 with nickel-62. A beam of positively charged carbon-14 ions was shot at a nickel-62 target at about 10% the speed of light. When these two collided, they fused to form selenium-76, which is highly unstable and quickly decays into various different nuclei, one of which is arsenic-74. However, because of the speed of impact of the beam onto the target, arsenic-74 is created at a very high energy state, which means it is spinning very rapidly, or it has a high angular momentum, or spin. It decays to its ground state by emitting gamma rays. It emits them in little discrete packets, meaning it will emit a few different gamma rays, depending on what energy state it comes from, to go from high energy to ground. This reaction happens approximately one time every 100 nanoseconds. And in those 100 nanoseconds, it has more than enough time to decay from high energy to ground. So the detector array, shown in this picture, was set up to start taking data from a moment of gamma ray impact to about 100 nanoseconds after. And any gamma rays collected in the 100 nanosecond window are considered to be in coincidence. We then took this coincidence data and analyzed it using something called a directional correlation of oriented nuclei, or DCO ratio. If you'll remember, I said that the nucleus emits gamma rays to bring itself down to a lower angular momentum. But all gamma rays are not equal. Some will lower the angular momentum by 2, whereas some will lower it by 1. Gamma ray transitions that lower the angular momentum by 2 are known as quadrupoles, and those that lower it by 1 are known as dipoles. And they will emit different radiation patterns, which are shown here. These two different radiation patterns means that depending on where our detector is placed, we will collect these gamma rays with varying intensities. This graph displays the intensity of my most prominent dipolar transition, 153 kiloelectron volts, as shown in the 90-degree detectors, or as shown in the 35 and 145-degree detectors. Along the x-axis is the energy of the gamma ray. You can clearly see here is 153. Along the y-axis is the counts, or how many times that particular gamma ray was detected. The counts under the area of this curve are how we measure intensity. Now, the y-axis scales on these two diagrams are different, but the area under the curve for the 35 and 145-degree detectors is approximately 14,000 counts. On the 90-degree detectors, it's approximately 27,000 counts. If we put these through our DCO ratio, we can see this gives us a value of about 0.5. And 0.5 is about what we would expect for a dipolar transition. Returning to this side of the graph, you can see the DCO ratios that I have collected for many different transitions in this nucleus. Here's a large cluster of dipolar transitions in these two areas, and a cluster of quadrupole transitions shown in these areas. By taking these results, I was able to update the arsenic-74 level scheme so that spins are known for energy states up to about 2,000 kiloelectron volts, meaning that all of the spins in this area of the graph were previously unknown, but they have been determined by this study. This result is important because it tells us that the signature splitting graph was in fact accurate and correctly describes the behavior of arsenic-74. But if it was not a problem with our measurements, what other possible way could we explain this irregular pattern? The previous group who studied arsenic-74 has suggested that this may be due to an irregular shape of arsenic-74. Instead of a prolate or football-shaped deformation, which many arsenic isotopes display, it's suspected that arsenic-74 has a triaxial deformation, or that it's asymmetric about all of its axes.